a remote Kenyan field, a farmer named Amina handed a cheek swab to researchers, and the sequenced DNA revealed a surprisingly uniform stretch that repeats across continents. That tiny segment suggests a handful of ancestors repopulated the world after a catastrophic loss. How could such a minuscule group sustain an entire species for millennia? When Hu and colleagues fed 3,000 modern genomes into fitcoal, the algorithm spun countless ancestral trees and measured minute genetic differences. Each simulation converged on a deep trough around 900,000 years ago, implying a dramatic drop in breeding individuals. The consistency of that signal sparked both excitement and skepticism among geneticists. The model's confidence interval hovers near 1,280 people capable of reproducing, a number smaller than many present-day villages. Yet that tiny cohort apparently carried the entire human lineage for over 100,000 years. Such an extreme bottleneck would have magnified genetic drift, wiping out countless rare variants along the way. Fitcoal's timeline shows the population hovering at that low point for roughly 117,000 years, a span that includes repeated glacial-interglacial swings. During this era, the genome shows little sign of expansion, prompting questions about how these survivors organized themselves, found food, and avoided extinction. Paleoclimate cores from East Africa record a severe arid episode that aligns with the genetic bottleneck, when lake levels plummeted and grasslands retreated. Megafauna numbers dwindled, squeezing human groups into tighter bands and curbing reproductive output. Could such environmental stress alone have forced humanity to the brink? Archaeologists excavating sites dated to the bottleneck period report a sharp decline in settlement density and a simplification of stone tool kits. The remaining assemblages are tiny, with fewer diagnostic flakes than earlier layers. This material scarcity mirrors the demographic contraction inferred from the DNA evidence. Comparing ancient DNA from pre-bottleneck fossils with modern genomes shows dozens of alleles that existed thousands of years ago, but are now completely absent. The sudden disappearance suggests whole lineages were cut off, never to re-enter the gene pool, underscoring the severity of the population crash. A contingent of population geneticists argues the dip could stem from unmodeled migration pulses or selective sweeps, not a true crash. Their simulations produce similar troughs without any demographic bottleneck, urging caution before declaring near extinction. The debate remains open, and new data may tip the balance one way or the other. In a 2023 conference, Dr. Liu displayed a chart where the confidence bands ballooned once the sample fell below 2,000 genomes, making the depth of the trough wobble. Critics point out that 3,000 modern genomes, though impressive, still miss many African subpopulations. That omission could tilt the inferred minimum size upward, casting doubt on the exact figure. The debate hinges on whether the signal is real or an artifact of sparse data. Researchers mapped the same genetic dip onto a Papua New Guinean genome collected in 2019. The trough appeared just as deep as in a Siberian sample from 2021. The pattern repeats in East Asian and South American datasets, even though those peoples left Africa tens of thousands of years later. Such consistency suggests the bottleneck happened before any major out-of-Africa wave, trimming the entire ancestral pool. It raises the question, how universal was that crash? Field anthropologist Maya Patel recorded a flood myth among a remote Amazon tribe in 2022, noting striking parallels to a firestorm legend from a Saharan community documented in 2018. If a single, small community survived a climate catastrophe, its story could have traveled with migrating groups, seeding similar motifs worldwide. Those shared narratives might be echoes of a real demographic squeeze rather than mere coincidence. Could myth be the cultural residue of a demographic bottleneck? A 2024 study of type 2 diabetes risk alleles found that a particular variant appears in nearly 1 in 3 Europeans, but is rare elsewhere, matching the pattern expected from a founder effect. The same variant shows up in African genomes at low frequency, hinting it survived the ancient squeeze and expanded later. Such amplified disease-linked genes illustrate how a tiny breeding pool can echo through millennia of health outcomes. Might our modern ailments trace back to that prehistoric bottleneck? Excavators at the Cima de los Huesos site uncovered a hominin femur dated to 850,000 years ago, and a team is now attempting to retrieve ancient DNA from the bone's dense inner cortex. If successful, the genome could reveal whether genetic diversity had already collapsed by that time. Direct evidence would either bolster fitcoal's statistical inference or expose a more complex demographic curve. Will those ancient fragments finally settle the controversy? In 2017, researchers identified a subtle dip in Neanderthal genomes around 600,000 years ago, a milder bottleneck that left a faint signature. The 900,000-year event described by fitcoal dwarfs that earlier squeeze, yet both episodes show Homo sapiens' knack for rebounding after crisis. Each crash reshapes the genetic landscape, pruning some lineages while amplifying others. How many hidden bottlenecks might still lie buried in our DNA? Dr. Alvarez examined the fitcoal output. She noted the scar of just 1,200-odd breeding individuals, a figure that feels almost mythic in its narrowness. From that slender thread sprang the vast tapestry of languages, tools, and cultures we see today. Recognizing such fragility forces us to rethink the narrative of inevitable progress. Does knowing our species once teetered on the brink change how we face future challenges?